Hi, my name is Michael Zeng, and I will be presenting an exploration of affine geometry and variations of the game of set. Is a project completed by Dr. Coco and myself. Before we talk too much about the game of set, let's talk about the history of the game of set. It was invented by Marcia Jean Falco in 1974 while she was conducting genetic research on German Shepherds. She was actually trying to establish whether or not epilepsy was hereditary in German Shepherds. And so, to keep track of the dog's different characteristics, she started using symbols instead of words to save time, and she had a lot of fun matching up the cards in different ways, and this led to the creation of the game of set. And so now we can start talking about aspects of the game of set and how the game operates. So the first thing we talk about is the deck and the playing field. So the deck is an 81 card deck with 4 characteristics on each card, and each characteristic has 3 variations. So it's this number of characteristics and variations that leads to the total of 81 cards that's so different from a standard deck of cards. And so right here we have a picture of a few cards. As you can see, each card has a fill. As you can see, the different fills are aligned, solid, and empty. Each card is a symbol, oval, diameter, squiggle, a color, red, green, or purple, and an amount of symbols, 1, 2, or 3. And so it's these variations that create the number of cards in the deck. And that's important to remember because it's the variations that are very important to playing the game set. And so the playing field is 12 cards taken from the deck. And the playing field is important because the number of cards in the playing field varies on whether or not you can find a set. And so if a set is found, or if there are no sets available in the deck, then you add 3 cards to the deck. But if the number of cards in the deck is above 12 when a set is found, then no cards are added to replace them, as opposed to if there were, say, 6 cards in the deck, they would need to be replaced. So that is an important distinction to remember when playing the game. So now we can talk about what a set is, which is basically the entire game. And a set of cards is 3 cards that are either all the same variation or all different variations for each characteristic. So as you can see here we have 3 cards that are in fact the set, because they're the same in the color, the shape, and the number of symbols. They're all exactly the same, and the one thing that they're not the same in, they're all different from each other, and that's the fill. If 2 things are the same and 1 is different, then it cannot be a set. But if they're all different or all the same, then it can be a set. So now how to play. The goal of the game is to get as many points as possible. The one with the most points at the end of the game wins. 1 point is given for finding and taking 1 set. There are no turns in the game set. If someone sees a set, they say set and take it, so sets are just taken from the game. If it's a set, then they take it and the cards are replaced as they need to be, and the player gets 1 point. But if it is not a set, they lose a point. So that's important to remember, that there's a punishment for losing, or for being wrong about a set. And so the game ends when the deck is empty and none of the cards in the playing field can make a set, and then whoever has the most points wins, as I said before. So what were we looking for in this family game? We were focused on finding the largest set of cards with none of them being able to form a set. Some of our sources were able to prove this using maximal caps and affine spaces, but we were able to use that to our advantage to work on finding other, sizes, maximum sizes of these sets. We attempted to combine affine geometry and coding to learn more about the behavior of the maximum sizes of playing fields in game set. We simulated tons of games and attempted to use those simulations in the maximum sizes of the playing fields in those simulations to learn more about the way the game behaved and the way these maximum sizes of sets of cards with no sets behaved when different rules were changed. So to understand affine geometry and how that can be applied to the problem, how it was applied in some of our sources, we need to look at what Euclidean geometry is. And Euclidean geometry is really just based off of Euclid's 5 postulates. So now we get affine geometry by removing the 3rd and the 4th postulate. And for us, what this is very important for is that it removes, or it doesn't remove, it changes what collinearity looks like. And so now things that are not collinear in Euclidean geometry are now collinear in affine geometry, and this becomes very important for how we identify sets in the game of set. For the coding, we used Python 3.8, and we just used basic for loops, while loops, and if statements. We ran thousands of games. We just carded the cards were represented by a list of each number represented a variation, and each characteristic had a index in the list. And so each card was a list, and then those lists were put into one big list that represented the deck, and then 12 cards were randomly chosen to create the playing field, and the game was simulated. So now a little bit more about how the code itself ran. As I stated before, we assigned each variation a number and each characteristic an index in the list. But how this can also be translated is if we observe them as points, each characteristic is a dimension, and then each variation is just like a value of that. So when we're used to x and y, now we have symbol, color, field, number. And so now if we put those in an affine space, we can use affine geometry to help our problem. But right now we're going to continue looking at the code. Just a little get too far ahead of myself. And so we were able to use these numbers for each characteristic and use addition mod 3 to identify sets. So if for each characteristic, say we start with the symbol, we took 3 cards, we look at the numerical value of their symbol. We do addition mod 3 for those three, and if it's 0, then we check the next characteristic, and then the next one. And if they all are 0, then it's a set, but if one of them is not, then it is not a set. I mean, this was something that was proven by Dr. Wan, which is one of our sources. And as I was talking about earlier, the usage of affine geometry. So now we have, if we can think about it, I guess a 4-dimensional space, and these points are in this space, and now now we can observe these points and their collinearity, and it turns out that when you take 3 cards that are a set and take their point translations and observe them in an affine space, they are collinear, and vice versa. And 3 collinear points in an affine space, their card representations in the game are a set, which is very interesting. And so that's why we can use affine geometry and maximal caps to observe the maximum size of sets of cards, because a cap is a set of 3 points that are not collinear, and a maximal cap is the maximal size of the set of caps. So in the standard game, which would be an affine space AAG 4-3, the maximal cap is 20, so our maximum size of a set of cards with no sets is 20, based on the relationship between affine geometry and the game, which is very interesting. So now I can talk about our results. I'm running out of time a little bit, so this is gonna be brief. We just changed some of the rules and made observations about large numbers of simulations of the game. Under the standard rule, the largest any playing field got, which would be the largest set with no sets, in the standard rules was about 15 to 18. With no variations of each characteristic can be the same. That is, like, they can't all be the same color. Each characteristic has to be different. That limited the number of sets that were available in the game, so naturally that drove this largest size of sets with no sets of cards with no sets up. This introduced an interesting impact of the addition of cards, where like adding 3 cards versus adding 1 card when there are no sets in the playing field makes no real difference. I think I'm really running close on my time here, so I'm just gonna have to kind of skip the end. You can read them. And so our conclusion, we were able to make good progress on the problem, I think, and make some good observations, and we'll be able to go further in the next semester as we continue with our research. But there's definitely more to be learned with the game and how it is tied to affine geometry, and more to explore, and the impact that coding can have on this problem, for sure. Thank you. On here are my sources.